So now that we have a basic understanding of some of the definitions behind second or higher order differential equations, not just second order, but higher order, we're going to talk about how we can find those solutions. I'm going to first look at how do we find solutions to homogeneous differential equations, higher order differential equations. The first thing I want to just mention is we can do something called reduction of order. And that is that if you happen to know what one of the solutions is, you can actually find the other solution. And sometimes we can find one just by guessing what we think it could be, and then using that to find the other one. So this is a very powerful method for finding solutions, is if you can figure out what one is, then you can find the other. If we're talking about a second order differential equation. They get a little bit more complicated when we get higher order. Same process still kind of works. You'd have to know two. If you had third order differential equation, you'd need to know 2 out of the 3. But let's just go with a second order. It's much easier, and we'll work on how to do that. So we're going to look at a second order differential equation. We have some constants times y double prime plus a constant times y prime plus a constant times y equals 0. It is a homogeneous. The solution is y is equal to c1 y1 plus c2 y2. And if you know y1, you can again find y2. So we're going to talk about that method of how this works. We do have to assume that y1 is a non-trivial solution. In other words, it can't just be y1 equals 2 or y1 equals 0. It has to be something more than that. And then when we do that, if we have this non-trivial solution, we can actually take a ratio of y2 over y1. That ratio will be another function. We'll call it u, for lack of something else to call it. So y2 of x is equal to y1 of x times u. And so if I know what y1 is, if I can figure out what this u is, I can find out what y2 is. And that's the whole process behind this, is we're going to try to figure out what that is. So let's see how we go about doing this and what it looks like. And the best way is just to kind of do an example. So let's take an example. Find the second solution y2 for y double prime plus 2y prime plus y equals 0 if y1 equals x e to the minus x. So again, what we're going to do is we're going to guess. We're going to basically say y2 is u times y1. And what we're going to do is we're going to kind of figure out what that u is, and then figure out what the value is. All right, so if y2 is equal to u times y1, y1 is x times e to the minus x. So y2 is u times x e to the minus x. If I know that this is my solution, if I know y1 is a solution, in other words, it satisfies this differential equation, then I'm saying y2 is also a solution and will satisfy this differential equation. So as we've always done, plug it in, which means I need to know what y1, y prime is. So y prime would be, well, this is a product. In fact, it's multiple products. But we're going to have u prime times x e to the negative x plus u e to the negative x plus minus u e to the x e to the negative x. So minus u x e to the minus x. So that would be what y prime is equal to. Then we can find what y double prime is equal to. And this again is just y2. And so that would be y double prime x e to the minus x plus y prime e to the minus x plus y, doing that, minus y prime x e to the minus x plus u prime e to the minus x plus u, or minus u, e to the minus x minus u prime x e to the minus x minus u e to the minus x, and then plus u x e to the minus x. So let's see if we can combine some terms here, see if we can't get this to look a little bit nicer than it does right now. So we've got a y double prime x e to the minus x. That has no like terms. We have a u prime e to the minus x, and we have a u prime e to the minus x. And we have another, nope, that's it. So we have two of those. So we have a 2u prime e to the minus x. We have a minus u prime x e to the minus x. We have a minus u prime x e to the minus x. So we have a minus 2u prime x e to the minus x. We have a minus u e to the minus x, and a plus u x e to the minus x. Oh, nope, they're not the same. So we have a minus u e to the minus x and another minus u e to the minus x. So we have minus 2u e to the minus x. And we have a 2 u x e to the minus x at the end. Okay. So here's what we have. And again, now what we're going to do is we're going to plug those in to our differential equation because it should be a solution. So we're going to plug this in. We have my differential equation again was y double prime plus 2y prime plus y equals 0. We're now going to plug in for the y2. So I'll just make this y2 just so you remember you're plugging those in. So we have u double prime x e to the minus x plus 2u prime e to the minus x minus 2u prime x e to the minus x. I must have made a mistake because I think I should have something go away. So let's just look here for a moment. So I have a u, positive u prime, let's see what I'm doing wrong. I know I have an error because things should have canceled out for us. So let me make sure I didn't get anything else that should have gone away. Okay, the first derivative is correct. It's the second derivative. Something got wrong. So let's just check to see what that would be. So the minus u e to the minus x. Let's see. So u double prime x e to the minus x, u prime e to the minus x, minus u prime x e to the minus x, plus u prime e to the minus x, minus u e to the minus x, and then minus u prime e to the minus x e to the minus x, minus u e to the minus x, plus. I'm not seeing a mistake, but I know there's a mistake because I know things should have canceled out. Or maybe they shouldn't cancel out. Maybe it's coming later. All right, let's keep going. I'm pretty sure I've got everything right. So we're putting these values in. So we've got u prime x e to the minus x, this 2u prime e to the minus x minus 2u prime u prime x e to the minus x minus 2u e to the minus x plus ux e to the minus x. Then that's going to be plus 2 times y prime. Y prime was this u prime x e to the minus x plus u e to the minus x minus 2 u e to the minus x. So that would be so we had u prime x e to the minus x plus u e to the minus x minus ux e to the minus x, and then plus the y, and our y was just ux e to the minus x, and that's supposed to equal 0. So now let's go ahead and collect like terms. This is where I think I'm collecting like terms and where they're going to be. So I have a u prime, or u double prime. I'm not going to have any other u double prime. So we have u double prime x e to the minus x. I have a 2u prime e to the minus x. I have a minus 2u e to the minus x. Right, I've got a 2u prime e to the minus x, and I have a minus 2u. Now I have another 2u prime. I know things are supposed to cancel. Oh, no, those are supposed to cancel. Okay. So collecting those like terms together, I have a 2u prime e to the minus x, and I have everything else goes to 0. So when you look at this and you collect all your like terms, so I've got this u prime x e to the minus x. I have a 2u prime e to the minus x. Minus 2u prime x e to the minus x. Oh, and here we go. This is where it goes. So this minus 2u prime x e to the minus x is going to cancel this one here. We have a minus 2u x e to the minus x, and we have a u x e to the minus x. So that's going to be one, and then we have another one here. So these all cancel. And then we have a minus 2u e to the x, and we have a plus 2u e to the x, e to the negative x, sorry. And those all cancel. So now I see that I have just this 2u prime e to the negative x and this u double prime x equal to negative x, and that equals 0. So we just collected all of our like terms, and we have this. So one thing I notice is I just have a y double prime and a y prime. So what we're going to do is we're going to let, and you can call it anything you want. I'm going to call it w. We're going to let w equal u prime, which means w prime equals u double prime. So we can now basically, and this is why it's called reduction of order, is we've just taken the second order differential equation, because this is a second order differential equation, and we just basically made it a first order, because I'm going to let w be u prime. So we have 2w e to the minus x equals 0 here. And this u double prime is now w prime. So u double prime becomes w prime x e to the negative x. So we now have a first order differential equation, which you actually already know how to solve, because we've been solving these before. So one of the things I notice is that I have an e to the minus x in all these terms, so I can pull that out. So I've got w prime x plus 2w equals 0. E to the negative x can never be 0, so you can just get rid of that. So we have w prime times x plus 2w equals 0. You can either solve this using the integrating factor method, or you can solve this using separation of variable. It's separable. I don't care which way you do it. I'm going to go ahead and do it with integrating factor method. So I'm going to divide through by x. So when I do that, my integrating factor is e to the integral of 2 over x dx. So that'd be e to the 2 natural log of x. So that'd be e to the natural log of x squared. So that's x squared. So my integrating factor is x squared, so I have x squared w prime plus 2xw is equal to 0. And so then I've got the derivative with respect to w, sorry, with respect to x, sorry about that. So the derivative with respect to x of my x squared times w equals 0. So taking the integral of both sides, we get x squared times w equals the integral of 0, which is just a constant. So we get w is equal to the constant over x squared. Well, remember that was u prime. So u prime is your constant over x squared. So that means u is the integral of that. So the integral of that will be my constant minus my constant over x, which you can just take that constant into it. So just the constant over x. All right. Now we're going to have lots of different constants in this. So let's call this one C1, just so we don't get confused. And so there's what my u is. My u is my constant over x. Let's let C1 equal something. Let's call it 1, because it just makes life easier. So therefore, my u is just 1 over x. And so that means y2, remember y2 was my u times x e to the minus x. So it's going to be 1 over x times x e to the minus x. So it happens to be e to the minus x. So I happen to now know what y2 is equal to, which means I now know that y is equal to c1 times y1, which was x e to the minus x, plus c2 times e to the minus x. The reason I let this y, this constant equal 1, is because my solutions there are constant free, because the constant comes in when I make my y, my total final y. These individual constants, this y1 and y2, these should be constant free. If I didn't make it constant free, I would just be putting that constant in there with that C1 right now, or C2 right now. So it wouldn't have made, I could have made it 5 if I wanted to, and then I have a 5 C2, which is just a C2. So that's why I can do that. It's just making this be something just to make it easier, and I'd be taken in with that constant anyway. But there's my solution to that differential equation, because I happen to know what one of the solutions was. Okay. Let's try one more. Let's find y2 for x squared y double prime plus 2xy prime minus 6y equals 0 if y1 equals x squared. So again, I'm going to let y2 equal some constant, some function u times y1. So y2 is equal to u times x squared. I then want to find out what, plug it in, and I know it's a solution, so I know it has to make this true. So I need to find y sub 2 prime. Well, that'll be u prime times x squared plus 2ux. And then I need to find my second derivative, because there's a second derivative in my equation. So that'd be y double prime x squared plus 2u prime x plus 2u prime x plus 2u. So there's my derivative. My second derivative, I can actually collect some like terms here. I notice I have 2 of these, so I have 4u prime x plus 2u. All right, and then all I gotta do is plug it into my differential equation and find out what I get. So again, my differential equation was x squared times y double prime plus 2x times y prime minus 6y equals 0. I'm going to be plugging y2 in here, so I'll make these 2's in here just to remind me that's what I was doing. So I have x squared times u double prime x squared plus 4y prime times x plus 2u. Did I call that y prime? 4u prime times x plus 2u minus 6 times y2. y2 was u, whoops, forgot my next term. Sorry about that. Minus plus 2x times y prime, which was u prime x squared plus 2ux plus my minus 6, minus 6 y2, and y2 is u times x squared, and that's going to equal 0. So again, I'm now going to multiply everything together and collect any like terms. So I have a u double prime x to the 4th plus 4u prime x cubed plus 2ux squared plus 2u prime x to the cubed plus 4ux squared minus 6ux squared equals 0. And now we're going to go ahead and collect like terms. So I have a u double prime x to the fourth. I have 4u prime x cubed and a 2u prime x cubed. So I have a 6u prime x cubed. I have a 2ux squared, a 4ux squared, and a minus 6ux squared, which is 0. This should always happen. You should always end up with a u double prime, a u prime, and then no u. If that doesn't happen, it means you did something wrong, and go find out what it was. So this should always happen to where this occurs, because now you can let, and again, you can call it anything you want, but let's let w equal u prime, which means w prime is u double prime. So we now do some substitution here. So we now have w prime times x to the fourth plus 6 times w times x cubed equals 0. And so when I look at here is I see that I have, again, a linear equation. I'm going to divide through by x to the fourth. I am assuming that x is not 0 here. So I have w prime plus 6x to the minus 1 times w is equal to 0. All right. So again, that means I'm going to do integrating factor because it's linear. If you want to do this, it also happens to be separable. You can do either way. It doesn't matter in this case because it equals 0. So we're going to go ahead and find our integrating factor. That'll be e to the integral of 6x to the minus 1 dx. That'll be e to the 6 natural log of x. And that'll, of course, be x to the 6th. Okay. So we're going to multiply through by that. And then we're going to get the derivative with respect to x of our integrating factor, x to the 6th times w. And the reason I went straight to here is because I was going to multiply through by x to the 6th, and I'd get to this step because this is 0 on this side. So I didn't need to show that step. Taking the integral of both sides, we get x to the 6th, w is equal to some constant c. So w is equal to c over x to the 6th. Again, w is equal to u prime. So u prime is equal to c x to the 6th. So u prime is c x to the negative 6. So u is going to be negative 1/5 c x to the negative 5. Again, this negative 1/5 times c, we can actually just make this all into one big constant. Let's just call that constant 1. And so we've got 1 times x to the negative 5. And again, we can do that because when we go to write the equation, y sub 2 is going to be that u times y1. And y1 was x to the squared. So it's going to be 1 over x to the 5th times x squared, or 1 over x cubed. And then we can say, well, y is now equal to c1 times x squared plus c2 times x to the minus 3. And again, the reason we can make this into 1 is it would have just been incorporated into that constant in the end. And so it all works out. All right. So this is how we do reduction of order.